What's up, my stat stars? In this video, I'm going to start helping you prepare for the AP Statistics exam in May. What I want to do in this video is walk you through some multiple choice questions that cover probability, random variables, and probability distributions. Now, these types of questions usually take up about 10 to 20% of the exam, which potentially could be a really big chunk. And probability and random variables are where kids make a lot of silly mistakes. So watching me solve these problems is going to be really beneficial to helping you prepare for the exam. Now, I promise you that none of these questions I'm about to go over are the exact same questions you're going to see on the exam, but a lot of the same concepts, key ideas, are what you will see on the exam. So watching me walk through them is going to really help you prepare for the exam. So before we dive too deep into looking at some practice multiple choice questions over probability, random variables, and probability distributions, let's talk about some formulas that are on the AP Statistics formula sheet that are going to really help you when it comes to this topic. So this is exactly what you're going to be seeing when you open up that formula sheet for the probability distributions. Now, at the very, very top here, we have some awesome formulas that are going to be very, very helpful. First, this is the probability of A or B. This is an awesome formula because you could use it in so many different ways. But remember, this union symbol means or, so the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Now, this formula is very useful because there's 4 things in this formula, and maybe you're given 3 and you want to find the other one, as long as you kind of just know how to plug things in and use algebra to solve. But let's talk about a couple other things here. So what's the opposite of this? Because there's actually a 5th formula that's here that you don't see, but it's actually there. The opposite of A or B is neither. So if you know the probability of A or B through this formula, then the opposite of that would be neither. Not A, not B. Now, another useful tool with this formula is if you know that A and B are mutually exclusive, that means they cannot occur at the same time. That immediately makes this back part a big, beautiful 0, because if they're mutually exclusive, that means there's no overlap. So A and B is equal to 0. Now, the other very useful thing is this. If you know that A and B are independent, again, this is only if A and B are independent, then that means that the probability of A and B is the probability of A multiplied by the probability of B. So it's another way that you could morph this formula around. But again, that's only true if it directly states in the problem that A and B are independent of each other. So again, a very useful formula in a lot of different ways, so make sure you know it and understand it. All right, the next formula that we have over here is the conditional formula for conditional probability. It says that the probability of A on the condition of B. So we're given B has occurred. We know B has occurred. What's the probability of A? Well, it's 2 parts. The numerator is the probability of A and B. The denominator is the probability of just the condition B. So pretty easy once you know how to use that formula. All right, then we have this little chart here that shows in the first line a discrete random variable. A discrete random variable is when the outcomes are finite and listable. So to find the mean of a discrete random variable, we simply take each outcome, multiply by its probability, and then add it all together. Now, you can also have your calculator do that for you, but again, it's pretty easy to take each outcome times its probability and add them all together to get the mean. Then we have the formula for the standard deviation of a discrete random variable. Slightly more complicated formula, but you take each outcome minus its mean, so you would have to find the mean first, square that result, times it by its probability, and then do that for every single outcome, add them all together, and take a giant square root. Now, it's a great formula, but to be honest, you should never actually have to use this formula on the AP Stats exam because your calculator can find the mean and the standard deviation of a discrete random variable for you if you know how to do it. All right, next up we have the binomial distribution. This is very, very common on the AP exam, so make sure you understand this. This is when we are given a set number of trials and we're trying to find the probability of X successes. Now, there's a couple rules here. We have to make sure that our trials are independent of each other. We have to make sure that the probability of success doesn't change. It stays the same. And we also have to make sure that on every trial there's only 2 outcomes, success or fail. Now, to find the probability of X successes, we first have this part right here, which just tells you how many different combinations it can happen. So if you have 10 trials and you're looking for 3 successes, you have 10 choose 3. It's going to tell you how many different combinations you can have with 3 successes out of 10 trials. Then we have P raised to the X. That's going to be the number of successes you have. So P is the probability of success raised to the number of successes you want. So in my example, it'd be P raised to the 3rd. Then 1 minus P is your probability of failure, just the opposite of success. And that's going to be raised to the difference between how many trials you have and how many successes you're looking for. So for example, if I have 10 trials, looking for 3 successes, 10 minus 3 is 7. So I got 3 successes, 7 failures are all taken into account for. But again, we also have some cool features on our TI-84 calculators with the binomial PDF and the binomial CDF that can make this formula pretty quick and painless. Then we have the mean of a binomial distribution. It's very simple. All you got to do is take the number of trials times the probability, nice and simple, and the standard deviation for a binomial distribution, square root of n times p times 1 minus p. Then we have the geometric distribution down here. The geometric distribution is where we're just simply looking for our first success. So if we're looking for our first success to be on the 7th trial, that means the first 6 were all failures, and then that 7th trial was our first success. So pretty easy formula there as well. We also have the mean, which is the average number of trials to get that first success, simply 1 divided by p. And then that number could vary because sometimes it takes longer, sometimes it takes shorter. So we have the standard deviation for the geometric distribution there as well. So I just wanted to go a quick overview of those formulas because these are on the formula sheet and they can be very, very useful. In fact, we might even use some of them on the multiple choice questions we're about to go over. All right, so let's dive into our very first question here. A company sells concrete in batches of 5 cubic yards. The probability distribution shows the number of cubic yards sold in a single order for concrete from this company. So we could sell 10, 15, 20, 25, or 30 cubic yards, and then we have the probability of each. This is a discrete random variable because we have a certain number of outcomes. We listed them, and we have the probabilities attached to each one of them. Now, they were very kind. They already calculated the mean for us. The mean is 19.25, and the standard deviation is 5.76 cubic yards. Now, we could have gotten that with our formulas, but they did it already for us. Now they introduce a new variable, y. Remember, that was x, the number of cubic yards, and here is the profit. The profit is 75 times the number of cubic yards minus 100. And they want us to calculate the standard deviation of that new variable y. Well, this is where we have to understand a really important concept. When you're working with means, multiplication, addition, subtraction all affect the mean. So if the question was, what's the mean of y? I would simply take 75. I'd multiply it by the 19.25 because multiplication affects the mean, and subtract 100 because subtraction affects the mean, and I'd get my new mean for the profit. But the question is asking about standard deviation, and standard deviation does not get impacted by addition or subtraction of a constant like the negative 100. So when it comes to standard deviation, all I'm going to do is take the 75 times the 5.76. Multiplication of a constant does impact standard deviation. I'm not going to add. I'm not going to subtract. I'm not going to do anything else. Definitely don't subtract 100 because that does not affect standard deviation or measures of spread. So if I do 75 times 5.76, I get $432 as my standard deviation for the profit. Option B there. All right. Next question, a complex electronic device contains 3 components, A, B, and C. The probabilities of failure for each component in any 1 year is 1%, 3%, and 4%. So the probability A fails is 1%, B fails is 3%, C fails is 4%. If any one component fails, the device will fail. So if any one of those fails, the whole device is not going to work. And the question is, if the components fail independently of one another, what is the probability that the device will not fail in 1 year? Okay, so if the device is not going to fail, I need A to not fail. Cannot fail. I need B to not fail. Cannot fail. If any one fails, everything else fails. C cannot fail. All right, so what are the probabilities? Well, again, if A has a 1% of failure, it's 99% not fail. B has a 3% of failure, it's got a 96%. Whoa, sorry about that. Did some bad quick math in my head there. Just looking ahead. If B has a 3% chance to fail, it's got a 97% chance to not fail. And if C has a 4% chance to fail, it's got a 96% chance to not fail. Now, how do I find the probability that A doesn't fail, B doesn't fail, C doesn't fail? Well, I multiply them. And why am I allowed to simply multiply these 3 probabilities together? Because they're independent of each other. What happens to A does not impact B, does not impact C. So all I got to do is multiply them together, grab a calculator, and you get 0.922 as the probability that all of them do not fail, which means the device will not fail. Option D there, or choice D. All right, next question. A nonprofit organization plans to hold a raffle to raise funds for its operations. A total of 1,000 raffle tickets will be sold for $1. After all the tickets are sold, one ticket will be selected at random and its owner will receive $50. The expected value for the net gain for this ticket is negative 95 cents. What is the meaning of the expected value? Now, another problem with discrete. They actually calculated the mean already for you, which is kind of nice. The mean and the expected value are the same thing. But basically, one person's going to win $50. One person's going to win $1. But we're talking about net profits. Everybody spent $1, right? So essentially, whoever wins the $50, they actually gained $49. And everybody else is going to lose $1. Make sense? Okay, and the probability that that one person wins is 1 out of 1,000 because only 1 out of 1,000 tickets is going to win, and everybody else is 999 out of 1,000. And if we want to find the expected value, which they already did for us, I'm just kind of walking you through to teach a little bit more in this video, we simply take each outcome, 49, times its probability, plus the other outcome, -1, times its probability. And again, we get that negative 95 cents. Now, what does the expected value mean? It's what we expect to happen on average in the long run. So if we were to play this game and play this game and play this game and play this game over and over and over again, 1,000 tickets, somebody wins. 1,000 tickets, somebody wins. In the long run, each person is expected to lose 95 cents per ticket, which is exactly what B says. It's the average that we would lose in the long run. Why is it a loss? Because it's negative. If it was positive, it'd be a win. But unfortunately, 99 out of 1,000 times, you're going to be losing $1. And only 1 out of 1,000 times, you're going to win that $49, which again, profit of $49. So again, it's an average and long run. That's exactly what expected value is, just like a mean. It's what we expect to happen in the long run for the average. All right. Next up, the commuting time for a student to travel from home to college campus is normally distributed with a mean of 30 minutes. Okay, this is awesome. The mean is 30 minutes. The standard deviation is 5 minutes. If the student leaves home at 8:25, what is the probability that the student will arrive at the college campus later than 9 a.m.? All right, so first off, the mean and standard deviation are in minutes. So how many minutes are we talking about here? They leave at 8:25. They arrive later than 9 a.m. That would be more than 35 minutes. 8:25 to 9 a.m. is 35 minutes. So we're trying to find the probability that the commute time is greater than 35 minutes. Well, if we didn't know that this was normal, we could not solve the problem. But because we are normally distributed here, we could go ahead and easily calculate our z-score. So 35 minus 30. Divided by 5. Pretty simple math there. That's going to be a z-score of 1. So asking about the probability that the commute time is greater than 35 minutes is the probability that a z-score is greater than 1. Since on the standard normal model, 35 minutes would be equivalent to a z-score of 1. To get that probability, I'm going to grab my calculator. You could use the normal model tables, but I like teaching the calculator. So I'm going to go second vars. I'm going to grab normal CDF. My lower value is going to be that z-score of 1, and we want to go greater than it. So I'm going to go to 99. 99 simply acting as my infinity. Leave the mean at 0. Leave the standard deviation at 1. That way I'm utilizing the standard normal model based on z-scores. And I get a probability of 0.159, or pretty darn close to 16%. So the best choice here is going to be A, 16% chance that it's going to take you longer than 35 minutes, which means you get to campus after 9 a.m. All right, a mathematics competition uses the following scoring procedure to discourage students from guessing, choosing an answer randomly on the multiple choice questions. For each correct response, the score is 7. For each question left unanswered, the score is 2. For each incorrect response, the score is 0. There are 5 choices for each question. What is the minimum number of choices that the student must eliminate before it's advantageous to simply guess? Okay, so let's see here. Let's see. This is a tough problem, so let's take it slowly. If they don't eliminate any questions, so if they just leave it away, so eliminate 0 questions. Now, the only way they're going to get 7 points, if they're guessing, is if they guess correctly, which is a 1/5 probability. Otherwise, they're going to get 0 points, and getting 0 points would be 4/5. All right, so what's the expected value here? What's the expected or the mean number of points scored in this situation? Well, we're just going to take each outcome, 7 times 1/5. Now, technically, you do need to do the 0 times 4/5, but I already know what 0 times 4/5 is. It's 0. So because that outcome is 0, I really don't have to multiply those. And 7 times 1/5 is 1.4 points. Now, that means if they simply guess, they are going to, in the long run, only get 1.4 points. So at that point, it's smarter to just guess because it's smarter to leave it blank because if they leave it blank, they actually get 2 points. If they just left it unanswered, they get 2 points. So in this situation, it's still better to just leave it blank. All right, well, what about if they eliminate one choice? All right, now if they eliminate one choice because they know it's wrong, now they have a 1/4 chance of getting that 7 points. Now that gives them a 3/4 chance of getting 0 points. Again, they eliminated one, but they're still going to guess between the remaining 4. Now again, what's the expected scenario in this scenario? What's the expected number of points in this scenario? Well, once again, we're just going to do 7 times 1/4. Technically, I need to do 0 times 3/4, but that's just going to be 0, so it doesn't matter. And 7 times 1/4 is 1.75. So once again, in the long run, if they eliminate one, it's still better to leave it unanswered, because in the long run, they're only going to get 1.75 points. They'd rather just leave it blank, because if you leave it blank, you get 2 points. So it's smarter to just leave it blank. All right, so let's move on to the next one. What if they eliminate 2 choices? Okay, now to get 7 points, that's going to be 1 out of 3, because you got 5 choices, but you eliminated 2 of them because you know you're wrong. So if you're just going to guess between those remaining 3, you got a 1/3 chance of guessing it correctly, and that means you got a 2/3 chance of getting it wrong. So again, what's the expected value or the mean number of points in the long run in this scenario? Well, 7 times 1/3. Technically, we do need to do 0 times 2/3, but that's going to be 0, so it doesn't matter. And 7 times 1/3 is 2.33. So now it's smart if we actually go ahead and guess now, because in the long run, we're going to get 2.33 points, which is greater than if we just leave it blank. If we leave it blank, we only get 2 points. So if we eliminate 2 choices in the long run and we just guess, it's smarter to keep going. It's smarter to just guess, because in the long run, we'll have an average of 2.33 points, which is more than what we would get if we just leave it blank. So the correct answer here is going to be C. If we can eliminate 2 choices, in the long run, we will expect to have 2.33 points, which is going to be greater than if we just leave it blank. So pretty good question there. Hopefully it made a lot of sense. And I didn't over-explain it or under-explain it, but that's a tough question that a lot of kids got wrong this year. So hopefully I did a good job of explaining it. In this problem, it says the probability that a new microwave will stop working in less than 2 years is 0.05. The probability that a new microwave is damaged during delivery and stops working in less than 2 years is 0.04. The probability that the new microwave is damaged during delivery is 10%, or 0.10. Given that a new microwave oven is damaged during delivery, what is the probability that it stops working in less than 2 years? Okay, for a lot of kids, they read this and their mind gets blown. There's so many different numbers given, so many different scenarios that sound very familiar. Stops working, breaks during delivery, like what's going on? So one thing I highly recommend doing in a problem like this is organizing your information. The first thing they tell me is that the probability that the microwave stops working is 0.05 or 5%. So notate that, the probability that it stops working. Like shorthand notate it, that way it's a little bit easier for you to understand. Then they said the probability that it's damaged during delivery, so I'm just going to write damaged, and stops working during the first 2 years is 0.04. And then finally, they said the probability that the new microwave is damaged during delivery is 0.10. So that would be just damaged. So they give us 3 different probabilities here. Okay, now the question is conditional. How do I know the question's conditional? Because I see that magic word given. Given that a new microwave oven is damaged during delivery, what's the probability it stops working? So for the conditional probability, we have that line. After the line goes the condition. What's given? Given that it's damaged. And then in front of it is what we're trying to find the probability of. We're trying to find the probability it stops working. Now, if it didn't give us the condition, if all the question said was what's the probability it stops working, well, then we'd be done. 0.05. That'd be the easiest question ever. But there was the condition attached. This is where that conditional formula that I talked about at the beginning of this video is going to come in huge. All right, in the numerator is the probability of both. The probability it stopped working and it's damaged. Well, I was already given that probability. That was 0.04. Again, that's your numerator, both damaged and stops working. We were given that probability, 0.04. That's awesome. In the denominator goes the probability of just the condition, which is just being damaged. And we were given that probability as well. The probability that the microwave is damaged during delivery is 0.10. And we're done. That's all we have to do to get our answer is divide those 2 probabilities. And of course, we get 0.40. So our final answer is choice D there. So again, it's a really easy question if you just process the information given to you, notate a couple of the probabilities, and then make sure you understand that you're given a conditional question and how to answer it using our formula. All right, and this question says the probability of winning a certain game is 0.5 or 50%. If at least 70% of the games in a series of n games are won, the player wins a prize. So let me explain what that means real quick. If you play n games, the only way you could win the prize is if of those n games, you win 70% of them. Now you might be like, well, I'm only supposed to win 50%. Yes, that's why to win, you have to do something special. And that something special would be winning 70% of the games over a course of n games. So now the question says the possible choices for n, the number of times you're going to play the game, is 10, 20, or 100. Which value of n should the player choose in order to maximize the probability of winning a prize? Well, we want to win, right? And the only way to win is to get 70%. And here's the law of large numbers. The more times we do something, the closer we get to the true probability. And that's the law of large numbers in a nutshell. So if we were to choose 100, over the course of 100 games, we would expect to get 50%. Because it's a large number of games, and over the course of more games, we would expect to get closer to that truth of 50%. But over 10 games, yes, we only expect to win 50% of them, so we only expect to win 5. But because it's only 10 games, less amount, we might have something special happen. So something special can happen in the short run. You might get lucky and win 7, 8, or 9 out of 10 games in only 10 games. It would be like tossing a coin. It would not be weird to toss a coin 10 times and get 7 heads. It wouldn't be weird. You expect only to get 5, but you're only tossing it 10 times. But the more you toss that coin, or in this example, the more you play the game, you would expect the true probability to settle down and get closer to that 50-50. So if we want to maximize our chance of winning the game, less series of plays is going to give us the greater chance of winning. So the correct answer here would be 10 games only. That's going to give us the best chance of winning. Still might lose, but that's going to give us the best chance. All right. Next question is a great binomial one. A recent study reported that 45% of adults in the United States now get all their news online. A random sample of 8 adults in the United States will be selected. What is the probability that 6 of the selected adults get their news online? So I'm given that the probability that an adult gets their news online is 0.45 or 45%. Now I do have to assume that that number is going to stay the same. It's not, what happens to the person. One person is not going to be impacted by the next, and we can assume that's true. And I'll talk about a little bit more about that in 1 second. We're also told our sample size is 8. So that means, again, whatever happens to that first person, whether they get their news online or they don't, is not going to impact the next or the next or the next person. That's the idea of independence. And finally, we're asked to find 6 total successes. Okay, so this is definitely a binomial situation. We have a probability of success that we assume will stay the same because we have independence, and we have a set number of trials or set number of individuals that we're going to look at, and that's 8. And we're looking for 6 of them. But the question is, which 6? Well, if here's my 8 people, there's 4, and another 4. Which 6 of them? Well, this could be the 1, 2, 3, 4, 5, 6. Those could be my 6 people. Or it could be 1, 2, 3, 4, 5, 6. Those could be my 6 people. Or it could be 1, 2, 3, 4, 5, 6. The whole point is there's multiple combinations of how you can get 6 successes out of 8. And that's where the formula comes in. So the first part of the formula that we talked about at the beginning of this video is 8 is the total number of trials you have, and then underneath it is how many successes you want. So we're looking for 6 out of 8 successes. So that immediately makes A and B wrong, and that means we now have it down to C and D, or E, excuse me. Next comes the probability of success. We have 0.45, and we need that to happen 6 times. So we need 6 people to get that 0.45. And again, look at my examples here. Those would be my check marks. Every one of those check marks would be 0.45, so that'd be 0.45 to the 6. Now, there's still 2 people left, and those people do not get their news online. Well, if there's a 45% chance that you do get your news online, then there's a 55% chance you do not, and that's for the remaining 2 people. 8 minus 6 is the remaining 2 people that would not get their news online. So there's my final result, which makes the only answer that is correct here, choice D. Hopefully that made a lot of sense. Now, we're done with the question. We got it right, but I also want to talk about how to actually get this probability. Now, multiplying 0.45 to the 6 times 0.55 to the second is pretty easy to do on your calculator, but where do I go to get 8 choose 6, the number of combinations? Well, let me show you real quick. First, you got to type in the number 8 first. Then you hit math, slide over to PRB, and you're going to go down to option number 3 for combinations. Oh, I went a little too far there. And then after it pops up, notice how to put the 8 in there. Now I'm going to type in the 6, and it tells me that there are 28 different combinations of how you can have 6 out of 8 successes. Now I'm going to take that 28, I'm going to multiply it by the 0.45 raised to the 6, and I'm going to multiply that by the 0.55 raised to the second for my failures, and I get my probability. But that took a hot minute. There's an even easier way to do this if you know how to use binomial PDF. So if you hit second vars, we're going to scroll down till we get to binomial PDF. And binomial PDF will do exactly what you tell it to do. All you got to do is fill in the given information that I already wrote on this form here. So how many trials are there? That's the 8 total people. P is the probability of success, 0.45. And then the X is how many successes you're looking for. If I'm looking for 6, all I got to do is type in a 6 there. And the binomial PDF will do exactly what you tell it. So again, hit it twice, sorry. Notice that you get the exact same answer I got, but a lot faster. Now, if you're wondering what the binomial CDF does, binomial CDF has the same setup, trials, success, and then X. But when you do a CDF, it's going to do the number you tell it, and it's also going to add into that any outcome below. So if I would have done a binomial CDF here, it's going to do 6, but then it'll also include 5, 4, 3, 2, or 1 successes as well. So it's going to accumulate everything that number or lower. But we did not need that for this question because we were asked for exactly 6 out of the 8. All right, so that was a quick review over a pretty easy binomial problem. All right, this next question is going to take me a moment to explain because it's actually a pretty tough one. At a small company, 40% of the employees are classified as junior level, and 32% of the employees work in Department A. Of those classified as junior level, 55% work in Department A. One employee will be selected at random. Now, before I read the question, I want to note that this last one is a conditional probability because it says of those that are classified as a junior level. So they gave me a condition, which made that a conditional probability or a conditional percentage or a conditional proportion. All right, now for the question. What is the probability that the selected employee works in Department A and is not classified as junior level? Okay, let's start diving into this problem. I'm actually going to teach you 2 different ways to solve this problem. I'll do it one way and I'll erase it and we'll do another way. Okay, so one way is to just kind of think about what's given. First, we were told the probability that somebody is a junior level is 32%. So notice I'm just quickly notating probability, percentage, proportion that are a junior level is 32%. Then we were told I'm so sorry, I messed that up. Beep, back up. 40% are junior level. Sorry, I jumped the gun there. 40% are junior level. Okay, now for the probability that you are in Department A. So I'll put probability Department A, and that is 32%. And that next probability given to me, again, was conditional. It was the percentage of people that work in Department A of those that are classified as junior level. So when I have a condition, I'm going to put that line, and behind that line goes the condition. So of the junior level employees, the percentage of them that work in Department A is 55%. Okay, so now I could figure out how to do this problem nice and slow here. All right, so here's how I'm going to process this. First, let's diagnose this conditional probability. We know that that conditional probability comes from a formula where in the numerator is the probability of A and junior. And in the denominator is the probability of junior. Now, I already know that the answer, the conditional answer, is 0.55 because I was given that. What I don't know is that numerator, the probability that you are A and junior. Sorry for my slightly messy handwriting. But the denominator I actually already know. The probability that you are a junior level is 0.40. So what I could do here is I could quickly solve for the probability of being in Department A and being a junior level. So all I got to do is take 0.55 and multiply it by 0.40. So 0.55 times 0.40. And I get 0.22. So there's a 22% chance that the person is in Department A and is a junior level employee. Okay, but the question says, what's the probability that the selected employee works in Department A and is not classified as junior? Well, that's not what I found. What I just got done finding was the probability that they work in Department A and they're classified as junior. But I could still find the question or the answer to the question by thinking about it like this. I know that 32% of all employees are in Department A. I just found out that 22% of them are junior level. That means the remaining 10%, the difference between the 32% of all employees in Department A, and again, 22% of them are also juniors. That means the other 10% are not junior level. So there's your answer right there. 10% are in Department A and not classified as junior level. But again, that took me a lot of thinking to get through that problem because I couldn't directly find it. I had to kind of indirectly find it by thinking about what was given to me and how I could take that conditional probability and solve for something. But then even what I solved for, I actually didn't need. I then had to kind of walk backwards a little bit to think about, okay, 32 total percent in Department A, 22% of those are also juniors. The remaining 10% would be not juniors. Now, another way to process this problem is with a tree diagram. So if you're more of a visual person, a tree diagram might help. All right, here's what we know. An employee at this company could be of junior level or not of junior level. Now, we were specifically told that there's a 40% of employees are junior level, which automatically tells us 60% are not junior level. Now, of those that are junior level, some of them are in Department A, and some of them are obviously not in Department A. Now, this is where that conditional probability comes in. We were told of the junior level people, 55% were in Department A, so we know that following the branch of if you are a junior level, the probability you are then in Department A is 55%, which means the probability that you're not in Department A is 45%. Now, we also have those same branches for the not juniors. Of the not juniors, some are in Department A and some are not in Department A. But we don't know any of those probabilities. We were not given any of them. We were only given a couple of these probabilities here. Now, the other thing we were told is that the total A, right? If I take all of this A at the end and all of this A at the end, we were told that 32% of all employees are in Department A. All right, so here's the deal. We already know that the end result of this branch would be junior and in Department A. And to get to that branch, we just got to multiply because the 55% is on condition that you were a junior level first. So 0.4 times 0.55 is the 0.22. So again, we already know that portion of the tree diagram. Now, what we want to find is this portion right here. And we don't know it. But again, remember, we do know that 32% in total are in Department A. So that means that this branch right here must end at 10%. Even though we don't know some of those conditional probabilities in between, we know that it has to end at 10% because we know in total the probability or the percentage of all employees that are in Department A is 32%. And if we already got 22% counted here of the junior level employees, that means of the non-junior, we got to have that 10%. So that's why the probability that you are not a junior level and you're in Department A following that very specific branch has to be 10%. So hopefully one of those two methods of explanation work for you and help understand it, but it seems like a very innocent problem that's actually kind of tricky to understand, so it's definitely a good one to talk about. All right, so as always, lots of good problems in this video, and they certainly don't cover every single probability question that you're ever going to be asked, but they do incorporate some really good ones that you might definitely see come up on the AP exam.